as long as it wasn't giving us an undefined, as when we were dealing with polynomials or rationals. Now, absolute values are a little bit different. Anytime we have an absolute value in calculus, how do we have to rewrite our problem? Piecewise. We have to do the piecewise every time. Okay, so let's rewrite the absolute value of x divided by x as a piecewise function. Okay, so we always have a case when x is greater than 0, when x is less than 0. Can x equal 0 in this case? No, because we can't divide by 0. Okay, so think about if you put in a positive number, does the absolute value change anything? No. So you would just have x divided by x, which is 1. So if we put in a positive number, we're going to get out 1. If we put in a negative, what does the absolute value do? It makes it positive, so it does the opposite. So if you take a positive divided by the negative, we should get a negative 1. For instance, if you put in like a negative 2, you would have 2 divided by negative 2. So we're going to get a negative 1 if we plug in a negative. All right. So if I wanted to do this limit, we would have to do the left and right hand limits. And we talked about if the left and right hand limits are the same, then the two-sided limit exists, right? So if I did the limit as we approach 0 from the right, which of these pieces am I on if I'm approaching 0 from the right? Greater than and positive. So what are we getting out no matter what there? 1. It's just like horizontal line. As you approach from the left, which piece are we on? Bottom, the negative 1. And we are getting out negative 1 every time. If you think about this graph, it looks like this. So, what would be the overall limit as we approach 0? Because the left and right hand limits are not the same. Okay. I want you guys to take a look at the next example and see if you can figure it out. I want to know if the limit as we approach 4 exists. So you're going to have to break it up and do a left and a right hand limit and see if you get the same thing. As you approach 4 from the right, that means it's bigger than, you're plugging in numbers bigger than 4. Which of the two pieces are you on? The first one. So that means we have the limit, we approach 4 from the right, of the square root of x minus 4. Okay. When we were talking about our limit laws, we had one Friday that said if you had a limit with a radical, you could bring that limit underneath the radical. Okay, so this square root, we can essentially think of this as the square root of my limit. All right, can you plug a 4 in then for the x? That's our direct substitution. So we get the square root of 4 minus 4, which is 0. If we approach 4 from the left, which piece are we on? Less than 4. So direct substitution says that's a polynomial. I can just plug in my 4. It doesn't matter when you're plugging it in if it's the left or the right. We can just put that in. And we get 8 minus 8, which is 0. So, does this limit exist? Limit as we approach 4 overall does equal 0. Alright. Is that okay? The reason that this square root one worked is that we were approaching 4 from the right, which meant I was putting in things bigger than 4, like 4.1, 4.01. Could you have approached 4 from the left here? because you would have things smaller than 4. So if I took like 3.9 and subtracted 4, I would get a negative. Could you do the square root of a negative? No. So we do need to kind of be mindful of that. All right, let's talk about this one. What do those brackets mean? Algebra 2. Remember the greatest integer function? Ooh. Remember? It was like greatest integer function, the graph was like stairs. So you could only get out integer answers. So integers -1, -2, 0, 1, 2. But you couldn't get out anything bigger than what you plugged in. So if we put in 0, 0 is an integer, so we would get out 0. But if I put in 1/2, 1/2 is not an integer. So my options are either 0 or 1, but you can't get bigger than what you put in, so we would still be getting 0. If I put in 0.9, I would get 0. But what happens when you put in 1? You would get out 1. So what did we put under here? So what was this? Stair step. So everything from 1 to 2 would be on this step, and then at 2 we would jump up, and so forth. Okay. So here's our kind of visual, and we could, just use the graph to evaluate this limit. We can also think through it. It just keeps following this pattern. If I wanted to see if this existed, I would have to do the left and right hand limits. If you're approaching 3 from the right, you're putting in something bigger than 3. So I'm putting in 3.2, 3.1, 3.01. What am I getting out every time? 3. If I put in like 3.1, that falls between 3 and 4. You always have to give me the smaller one, so that's 3. If I put in 3.01, it's still between 3 and 4. Smaller answer is 3. So in this case, we're always getting out 3. If we approach 3 from the left, I'm putting in things smaller than 3. So if I said 2.9, 2.9 is in between 2 and 3. What are you going to get out? 2, because you get the smaller answer. If I said 2.99, I'm still getting 2. So this one's giving me a 2. We could get that from the graph as well. If I am approaching 3 from the right, I'm up here on this step and I'm getting out 3 every time. But if I'm approaching from the left, I'm down here and I'm getting out 2 every time. So does the limit exist? Because the left and right hand limits do not match. Last thing that I want to talk about today is what's called the squeeze law. It's something we can do when we have a nasty function that we can't evaluate any other way. When we are looking at this, with limits, it is true. If you have a function that is always less than another function. Okay, so if I have, let's say this is function f, I'm going to put endpoints on it, and this is function g. Okay, would you guys agree that f was always less than or equal to g? So the same is true about the limit. No matter where we're at, the limit of f would have to be less than or equal to the limit of g. Okay. So the squeeze theorem is basically the same idea, but it applies to 3 functions. If we have some function f that we're trying to find the limit of, but our limit laws don't work. So we have limit laws for rational functions, polynomials, radicals, but we don't have any limit laws, for instance, for trig functions. Okay, so if I had something like that, if I knew some other functions, so let's say it was, I knew that f always fell between functions g and h. And if g and h were things I could find the limit of, I know that the limit of f would have to fall between them. Does that make sense? So that's what we're going to do. If we have something nasty, we are going to see, can we use things that we already know to find the limit? I am going to be very deliberate about the examples that we do on these. We are only going to do them with sine and cosine. Okay, so our squeeze law, I'm just trying to kind of teach you the general process. It's not something that's really used a lot in Calc 1. If you have to go on to take more calc, you'll need it, so I have to show it to you. But I'm just trying to give you a general understanding right now. So all of our examples are going to be very, very similar. The ones I'm doing with you are always going to have a sine or cosine. Now think about the graphs of sine and cosine. What values do sine and cosine always fall between? Well, that's the x, but think about your y values. When we graph them, they always bounce back and forth between 1 and negative 1, right? So if I asked you to find this limit, x squared sine of 1 over x, that is really nasty. We have to start with something we do know. So our work on this is the answer. I've already told you this limit equals 0. We are trying to justify that. So the steps are important. We know we have a sine, and we just said sine is always going to be between negative 1 and positive 1. Does it matter what your angle is when you're looking at the high and low points? No, the high and low points, remember, those are the amplitude. That's changed by a number out in front. Changing the argument just changed how quickly it repeated. So this angle could be anything I want. I am trying to make it match this. So what should I change my x to? I want it to look like this one. That's 1 over x. So it would be true that the sine of 1 over x is also between negative 1 and 1. Okay. So look at what we've got so far. I have gotten my sine and my 1 over x. What else do I need? An x squared. Now x squared is positive, right? So in an inequality, we could just say, all right, I'm going to multiply all this by x squared. It's a positive number, so it's not going to flip any inequalities. So negative 1 times x squared is negative x squared. Less than or equal to x squared sine of 1 over x. Less than or equal to positive x squared. So now I have the x squared sine of 1 over x. What's the next thing we need? The limit. So we are going to add a limit to each of these three pieces. Limit x approaches 0, negative x squared, less than or equal to the limit x approaches 0 of x squared sine of 1 over x, less than or equal to the limit x approaches 0 of x squared. I know this is killing those of you that don't like to show work, but it is important. We are almost there. I don't have any hope of doing this middle limit because I don't have any limit laws that apply to trig functions. But, can you do the limit as x approaches 0 of negative x squared? Yeah, that's a polynomial. So I can just plug in my 0 and what do we get? 0. So that limit goes away. This end is equal to 0. And what is the limit as x approaches 0 of positive x squared? 0. So my limit has to be greater than or equal to 0 and less than or equal to 0. So the only option is 0. We're just going to try a couple more. Okay. The first step has to be something we know for a fact. What is my first step going to be? Sine is between -1 and 1. Same as the last time. Okay, the second step. We are trying to build this thing. So I look, first difference is my angle. Does the angle matter when you're looking at your high and low points? No, so I can change that to whatever I need, which in this case is a pi x. What's the next thing I need? X squared. So we've got all this, we need the x squared. X squared is positive, so we can just multiply everything by it. So we get -x squared less than or equal to x squared sine of pi x less than or equal to positive x squared. Alright, now what do I need? The limit. We're trying to make it look like the other one. The thing we're missing is the limit. So we're going to add a limit to all three pieces. So then we know the limit as x approaches 0 of -x squared is equal to, we can't do the middle, and this end is equal to, so our overall limit has to be 0. The squeeze law only works if you get the same thing on both ends. Okay, if one of them was 0 and the other one was 1, that wouldn't help me at all. But if they match, then I know what my limit is equal to. Questions? Let's do one more. Best for last. Here we go. Isn't that gorgeous? All right. So, what do I do first? Sine is between -1 and 1. I told you I'm only going to do sine or cosine. Your first step is always going to be -1 less than or equal to sine less than or equal to 1, or -1 less than or equal to cosine x less than or equal to 1, just depending on if the problem has a sine or a cosine. Then the next step, you have to make your argument match the argument here. And you can change that argument if it doesn't change the high and low points. So -1 is less than or equal to sine of 2 over x is less than or equal to 1. So I have this part. What do I need next? The radical. Okay, square roots are positive, right? So I can multiply all of it by the square root of x plus x squared. So now I have all of this. We need a plus 1. In inequalities, can you add 1 to every piece? Yeah. So I have negative square root of x plus x squared plus 1 on the end. Now I have all of this. What's the next step? The limit. Okay. Alright. So now we have to see if we can evaluate these limits. Limit laws, we know we can bring the limit under the radical. Okay, so if I plug in, it's basically just a negative square root of 0 plus 0 squared plus, what's the limit as x approaches 0 of 1? 1. Limit of a constant is still a constant. So this whole side turns into 1. Okay, over here, if I bring my limit underneath, I can plug in my 0, and the limit of 1 is 1, so this side is also 1. So this overall limit is equal to 1. All right. So we are done with this section. You have the book problems on that last slide, which I told you yesterday you could start. We will have a work day for those tomorrow. Today, I have posted a handout on Classroom. This handout is mostly practice with like factoring and reducing things so you can plug in. So most of them are fractions, trying to evaluate your limit. There are no squeeze theorem on this handout. So it's only 8 questions. The handout is what's due tomorrow, but you have some time. So if you get done with that, you are welcome to work on the book problems. And then tomorrow we will just have a work day. I'm not teaching at all. And then the book problems will be due on Thursday.